Okay, let's begin. Test number 1 is on Tuesday, so we will spend a portion of our class today reviewing for the exam. Project number 2, all of you should have got that back from me. We'll discuss that very shortly. Are there any questions, though, before we begin? Okay, let's talk a little bit about project number 2. There's a few things that I want to bring up. First of all, overall the grades were good, but there were a few comments I wanted to make regarding project number 2. First of all, this is number 1D. So the first part here, the linearity of the regression function. Well, that's basically he's asking for to check, do we have x in the right form in our model? And the way that we make that determination is to look at a plot of the residuals versus x. And we look for particular kinds of patterns. Whereas some students were getting mixed up with was that the kind of pattern that they saw was one that corresponded to non-constant variance, not a problem with the linearity of x in the model. So to help explain that a little bit more, let's take a look at some plots here. So on the left-hand side, I have a plot of just y versus x that I've made up. And so the red dots represent our observations. Can everyone see the red dots? They look kind of small I'm looking at right now. That would be helpful if I didn't have this up here. Can you see the red dots? It's like you're going to a doctor's office and he asks you to look at certain things. Do you see the dots? Anyway, and what would the plot of the residuals versus x look like in this particular case? Notice how the residuals tend to be, well, that black line is supposed to go through the middle of the red points. So what would the plot on the residuals versus x look like? Of a random scattering of points. So you would expect to see something, oops, let's use red, this is a thicker one. You would expect to see, those are supposed to be points, something that looks like that. Okay? Let's look at another plot. So what do you think about here? What do you think the residuals versus x is going to look like? Is it going to be a random scattering of points? No. But what kind of trend or pattern should we see in the residuals versus x plot?
Negative.
Yeah, you're going to see some negative ones because of this. So you're going to see some negative ones down here. And then you're going to see some positive ones up here because of what you see here. And then you're going to see some negative ones again down here. Right? Okay. Obviously, we have a problem with the linearity of x in this particular model here. Instead, a better model would be something that looks like that. Okay, so the linearity assumption is violated here. Okay, here's another plot, y versus x. Just from looking at that, does it look like the linearity assumption is violated? No. That model goes through the middle of those points still. But what do you see as a problem, though? The variability of those points changes as a function of x. So if we were to look at a plot of the residuals versus x, you would see something that looks like this. Where, again, as a function of x, the variability of the residual changes. This is an example of non-constant variance, not a problem with the linearity. We have correctly specified x in this model, yes. The problem is with respect to this extra variability that we have as a function of x. That's the problem. So, with that as background then, When we look at, now in the project, we're looking at this particular plot to examine linearity. Do we have a problem with the linearity of x here? No. What we do see is that there's smaller variability here than there is out here. That has nothing to do with the linearity aspect. Nothing. So then the correct way to answer then this problem is that there is not sufficient evidence to indicate that there's a problem with the linearity of x in the model. And that's it. Then when we look at the residuals versus y hat now, this is to look at for the constant error variance problem. We see, smaller variability here than what we have out here. So thus we do have a problem with the constant error variance. Now you can see that the two plots that I have circled there look very similar. And the reason why this occurs is because we only have one predictor variable. Once we go to more than one predictor variable, you could have multiple plots of those and still only one plot like this. And depending upon the nature of this problem with the error variance, you may or may not see the same problem here as we did, or you might not see the same pattern there as we see in the other plot. So that's why we take the time to look at, obviously, both plots. Are there any questions? You need to make sure that you're looking for the right kind of pattern in these plots. The book details other example patterns, and we've looked at a variety of different patterns as well in class. Okay. So some students were having problems with that aspect of the project, another part of the project that I guess I was kind of surprised that students didn't look at was very few groups did this. Oops. When you were looking at the error variance aspect, very few groups actually look at the Box-Cox transformation. Now obviously, again, we can look at the residuals versus y hat. We can look at the BP test. We can look at the Levene's test, but a lot of groups forgot to look at the Box-Cox part. Well, notice the Box-Cox transformation lambda hat, 0.6. So what that says is that maybe you should consider taking y raised to the 0.6 power to solve the non-constant error variance problem. We can also look at the corresponding plot for the Box-Cox transformation. And I know it's kind of small, but what you can see there is that confidence interval does not contain 1. If it contained 1, then that might suggest to you, well, maybe no transformation is needed. Maybe there really isn't a problem with the error variance. But the interval does not contain 1, although it's close. It does not contain 1. Notice also, since this is close to 1, notice how that kind of also corresponds to what we see up here for the Levene's test and the BP tests. Both have p-values that would often be characterized as marginally significant. Because, if you took alpha 0.01, you say, don't reject. If you took alpha 0.05, you would say reject. So we have marginally significant values. Kind of, again, just to emphasize the point, kind of, again, corresponding to ones being very close to that upper bound of that interval. So then this leads then to, well, why did I take the square root taste as my response? Well, from looking at the Box-Cox. Sure, Box-Cox says 0.6, but what's more interpretable to you, typically? A square root transformation or something raised to the 0.6 power? Well, I think all of you probably more familiar with the square root transformation. So that's why I ended up taking it. And plus, of course, 0.5 was inside that interval too. And it seemed to help solve the problem of non-constant error variance. I'm not saying that it's a perfect solution, but we do see some benefits from it. You know, by looking at BP tests, Levine's tests, even I don't want to go there. When you take a look at the residuals versus the y-hat plot, let's actually go ahead and do that after the transformation. Just make sure that is after. Now, after the transformation, you do see a little bit extra variability, in particular right there. You know, it's somewhat hard to tell because, again, we only have a few observations in that portion of the plot. But it seems to at least help. P-values are larger for those corresponding tests, so I'm satisfied with the result. Are there any questions? Okay. A few more things. We went over this in class. I think there was a question about it. But some students still had, a few students missed it on the project, and that is, I asked you in part F, well, which confidence interval, the one that came about from using the model that had the square root of taste, or the one that you constructed in Project 1, which did not do any kind of transformation, which confidence interval is more likely to actually be a 95% confidence level? And I said, and the answer came, hopefully you've read it by now, is that it's a square root of taste. Why? Because the assumptions of your model are more likely to be satisfied. That's simply why. We have all these little mathematical assumptions going on in the background, you could say. And to say 95% confidence, the only way that works is if my assumptions are at least approximately satisfied. So if I have a violation of one of my assumptions, I need to start worrying about any kind of inferences that I'm making. It could be incorrect. What do I mean by incorrect? Well, when I say a 95% confidence level, maybe in fact it's not 95%. It's something else that you don't know what it is. So by saying simply that the confidence intervals are wider with this square root of taste model, that has nothing to do with judging which interval is better. Just because it's a wider interval doesn't mean it's better. So for example, let's say that let's say a confidence interval for the population mean, and let's say I have mu equal 5. And I have two different ways to calculate an interval. Method number 1 produces an interval that has, let's say, 4 to 5.5 as the limits. Okay? And let's say the other way that I calculate my interval is negative infinity to, let's say, 4.5. Now, obviously, interval number 2 is wider than interval number 1. Which interval is better? Number 1, because it actually contains mu. So that's a dramatic example of just because the interval is wider doesn't mean it's better. Okay. Lastly then, let's go to number 2. So the purpose of this problem was for you to see what would some of these plots and some of these numerical results that we're calculating look like if we knew that indeed all the assumptions of the model were satisfied. And I wanted you to get a concept of the idea of variability, that just because all the model assumptions are satisfied, you shouldn't expect some of these plots to look exactly like you want them to. So let's take a look at this. So here are some of the diagnostic plots. And remember, normality is indeed satisfied because we have controlled how the data comes about. We know that the normal distribution was actually used. But take a look at that QQ plot there. We see some deviations of these points from the line. And a lot of you got understood, well, why is this happening? Well, I only have a sample size of 30, and so, this QQ plot, it's hard to judge normality with a QQ plot or any other means with a sample size of only 30. And that even though we see a little deviation there in the tails of the distribution, it's not something to worry about. Now, where would I be worried? Well, if I start seeing something that was more dramatic, then I'd be worried. Also, if you were, let's say, really, really picky looking at these plots, and unfortunately none of you were really, really picky, because you knew, I think, in the end that, yes, everything should be okay with these plots. But let's say that you were really, really picky, and you didn't know that, indeed, that all the assumptions of the model were satisfied. You might, on this residual versus y hat plot, you might draw a line like this. So that one that looks like that. Okay. Is the variability supposedly changing as a function of y hats? Well, if I look at it that closely like that, you might be thinking, oh my gosh, I got a problem. No, you don't have a problem. And the reason is you need to take into the context of the fact there's only 2 observations right there. Okay? And so even though you see less variability, and that's one small portion of the plot, it doesn't mean you have a problem. Take into the context the variability, the sample size. And just to show you that indeed that the sample size of 30 here is playing a role, what I decided to do was show what would happen if I had a sample size of 900. Would the plots get better? And in fact, they do. So, look at that QQ plot, for example. That's dramatically better than what we saw before. But in both cases, assumptions of the model were satisfied. It's just the fact that now we have a sample size of 900 here. This is why this is working out, let's say, better. But, we again do see a little deviation towards the tails. Obviously not as much as before, but we see a little deviation. Again, not something to worry about. Where would I be worried? If I started, again, seeing something more dramatic. Maybe something that looked like that. Or maybe even stuff like up here instead. Take a look at the residuals versus y hat here. Again, we got a little bit there, but remember, the assumptions of the model are satisfied, in fact. Also, take a look at this. Uh-oh, we've got some points outside those red lines there. Should we be worried about outliers? No. If I have 900 observations, I'm bound to have some that are a little bit outside the limits. Excuse me? About 4, yeah. And I think when I went through the calculation here, actually 2.4. Well, what is this calculation representing? It's just an application of what you learned about in another class with the binomial distribution. That if I expect about, let's say about, what did I say here? If I had a normal distribution, what percentage of observations would I expect to be outside of plus or minus 3? And let me actually calculate this probability here. So this is a probability, let's say z is less than 3 minus a probability z is less than negative 3. 0.9973. That's the number. That's the proportion of observations that should be between there. Well, if I have 900 observations in total, then that says that 897.57 of them, somehow you can get that 0.57, on average should be within these values. So say that says that 2.5 of them on average should be outside the values. Not too far outside, but it's okay to be a little outside. And in fact, that's what we have. So this is a case where, we don't need to be worried. This is what we would expect. This is, I'm going to use this word, normal. Okay? Now, when would I be worried? Well, if I start having values maybe -5, +5, if you look at the normal distribution, it's very unlikely to be that far out, a standard normal distribution. If instead, let's say I was having 100, let's say 20 or 50 observations that are just outside of ±3, then I might start being worried too, because I know that's not what I would expect to have happen if my normality assumption was, if this all worked out. Now, what I would recommend that you do on your own is use this corresponding code that I have here, and actually simulate other data sets. So use different C numbers with n equal 30 and n equal 900, and see what happens. Especially with the n equal 30, I think it's important to do, because you're bound, if you simulate it enough times, you're bound to find some cases where, again, normality you might be worried about, or even the non-constant variance. But what that helps you then make a judgment about then is that when you don't necessarily know that the normal distribution is correct in actual problems, it helps you decide, well, is what I'm seeing, this maybe small normality problem I'm seeing in QQ plot, is that something I really need to be worried about with this kind of a sample size? Also, what you can do is with that same simulation program then, try other things where maybe the assumptions of your model are not satisfied. Try, instead of using a normal distribution for the epsilons, use a gamma. Use some other distribution. And see if these plots help you pick up that problem. Try maybe instead of using x in the model, use square root of x. See if these plots help you determine if there's a problem or not. We went through some examples like that in class, but we can't spend days and days and days simulating data to show you all the things that can happen. This is where it will be helpful for you to do it. And I guess just to emphasize my point here is that I guess for the next time I teach this course, I think for project number 2, that's what I'm going to have my students do. Give them this set of code and have them simulate some stuff. Okay. That's project number 2. Are there any questions? Okay, so let's talk about the test. Oops. Okay. Where are my notes? Hold on a second. There they are. So test number 1. Now, to help you out in case you have any last-minute questions, on Monday night from 9 to 10 p.m., I will be having virtual office hours in the chat room that's linked off of the course website. So simply put, I'll just be logged on, and you can drop into the virtual office hours and ask any kinds of questions that you may have. You don't have to, but if you want to, please feel free to drop by. Sorry it's that late at night. It's just that I have a 3-year-old son and a 4-month-old son, and I need to make sure that they're sleeping first before I can go back to work. And hopefully they will be sleeping by 9 o'clock. If they're not, it's probably going to be a long night. Anyway, so virtual office hours. The test itself, of course, will start at 11 a.m. on Tuesday, and let's go up until 12:25 p.m. Now, I've written the test for an hour and 15 minutes, but I'm going to give you an extra 10 minutes in case you need it. There's not a class, or at least I don't think there's a class that's meeting in here after us, so that's why we can go a little bit longer. So we have an extra 10 minutes. Remember the formula sheet. And the R handout sheet or whatever. Again, from the test web page, you can actually download it and take a look at the information that's going to be given to you. You do not need to bring that with you to class. I will actually pass out a paper copy to you. And again, the purpose of this is so that you don't necessarily have to memorize formulas. You don't have to memorize R code. The test, it's over, of course, chapters 1 through 3. And here's just a general outline of what the test looks like. There are 100 points possible, 3 problems overall. The first problem is 31 points, and it has 4 parts. Simply what I'm going to do is give you a data set, and then you're going to use R to find out some stuff about the data set corresponding to questions that I ask. So you might expect you're going to have to tell me what the sample model is for a data set. Okay? Problem number 2 is 36 points. There are 6 parts, and it's the same kind of format. I'm going to give you a data set. You're going to have to use R to help you answer questions corresponding to that data set. And then lastly, problem number 3 is 33 points, 4 parts, and these are all short answer questions where these parts are not necessarily connected in any way. So part A has nothing to do with part B and so on. So what's an example then short answer question of what I could ask? Here are 2. First one. Why do confidence intervals for the expected value of y get wider as the distance between a specific x of h, predictor variable value, and the sample mean of all the sampled x sub i's increases? So again, why do confidence intervals for the expected value of y get wider as the distance between x, corresponding thing that you want to do predictions at, and the sample mean of x's? As that distance gets wider or farther, why does the interval get wider? Why? It's not a rhetorical question. Well, what about the formula? That's the thing. You have to tell me why. So, this is a short answer problem. So you might have to, give me a few sentences. So what would you say?
The variance proportion to the square root of distance.
You have small x.
Excuse me?
You have smaller x when x is R from the mean.
Well, I think you're kind of getting an intuitive reason, which is that you have less information as you're getting farther and farther from the mean. Where in the mean, for x, that's where most of your information is. That's the center of your location. So as you get farther out, you have less information. How is information represented in a statistical context? Well, it's represented by variability. The larger the variability, the less uncertainty you have with the location. Okay. Here's how I actually answered it once on an answer key. I actually went to using the formula. I said the confidence interval equation is, I gave the equation, where, and I actually wrote out what var hat of y hat, which is used in that equation, what it looks like. And I said, notice that the xh is part of the numerator in the estimated variance formula. I guess it's not going to hurt me to write it out. Remember, of course, you don't need to memorize this formula because it's given to you on the formula sheet. Okay. So I said, notice that the xh part is part of the numerator in the estimated variance formula. As x of h gets farther away from x bar, this will increase the numerator and thus increase the variance overall. Because the variance increases and is added and subtracted from y hat after being multiplied by a t-distribution value, the confidence interval increases in width. So that would be one way to approach the problem. Another way would be to appeal to the intuitive reason for why this is happening too. So notice this took me 4 sentences. That's what I mean by short answer. Here's another short answer problem that I've given in the past. In general, what is plotted in a QQ plot? How does one know when a distribution assumption is violated when using this plot? First of all, notice that there's actually 2 questions for that. And an unfortunate thing that sometimes happens with students when they're taking the test is that they miss the fact that there's actually 2 questions and they will only answer one of them. So be careful about that. Here's the question again. In general, what is plotted in a QQ plot? How does one know when a distribution assumption is violated when using this plot? So what's plotted in a QQ plot?
Quantiles of the sample versus theoretical quantiles of the normal distribution.
Yes, so that's what you need to say. That's what's being plotted. Now how does one know when a distribution assumption is violated when using this plot? Someone else. You see the points deviate from the straight line. You need to go a little bit further though. Why do we look for points deviating from the straight line though?
Because if they're on it, they would be like the normal quantiles.
If they're on it, that says the observed quantiles are equal to the normal quantiles. The farther away means that these quantiles are not equal, and thus, maybe your data doesn't actually have this normal distribution property. So the way that I answer the problem is like this, similar to what we just said. A QQ plot plots the ordered quantiles for a particular distribution against the observed ordered quantiles for a variable in a data set using a simple scatter plot. If pairs of the ordered quantiles are different, there is evidence that the particular distribution is not correct for the data. Often on a plot, a straight line is drawn through the origin at a slope of 45 degrees. Points that do not fall close to this line indicate the distribution assumption is violated. Okay? So these are the kinds of responses that I'm looking for. Now perhaps as we were going through these 2 example questions, you knew what the answer was, but the problem was maybe you didn't know exactly how to word it. And this is why I ask questions like this, because I wanted to make sure that you can actually communicate, to me, or let's say after this class to someone else, what this stuff means. And so that's why I ask questions like this. In fact, you'll see similar structures to all my tests, where you have some data, you're going to analyze it, then at the end I always put these short answer questions. These short answer questions are usually my favorite parts of the test. I don't know if students think that, if this is their favorite part, but this is my favorite part of the test because it really allows me to narrow in on stuff to make sure that you do understand certain aspects of this stuff that we're talking about in the course. Any questions about that? Okay. Also on the exam, and what I laid out there for 1, 2, or 3, or at least parts of those problems, there's at least one homework problem. So it should look very familiar to you. And if it looks familiar to you, well, of course that means you've been doing the homework, and problems should be easy. Obviously, if you haven't been doing the homework, well, then this isn't going to help you at all. Maybe you should do the homework. So let's again talk about the structure of the test, since this might be a little bit new to some of you in terms of having some computer aspect to the test. At the beginning of class, what I will do is I will actually pass out a paper copy of the test. This is where you write all your answers on. You will not hand in anything electronically to me. You need to be using these computers here to help you answer particular problems on the exam. Again, you can think of R basically serving the role of a calculator that you would have maybe in other stat courses or math courses. And if R is needed for a problem, what you need to do is, write some code. Maybe let's say estimate a regression model, write some code, get the model out of R. If you maybe need to do like a confidence interval for the expected value y, write some code, get the confidence interval out of R. Now, what do you need to then write down on your piece of paper? Well, obviously, you need to write down the confidence interval. So you write down the confidence interval. But you need to go one step further. In other classes, when you haven't had a computer, what would you do? You would show your work. So how do you show your work here if you're basically getting the computer to do your stuff? Well, actually tell me what you are calculating. So what you could do is actually write out the corresponding formula. I'm not going to write it all out just at the same time. Write out the corresponding formula that shows me, okay, yes, you did know what the formula was. You know what you're trying to calculate. So I do need you to actually show me your work. I don't want to only see, let's say, numbers written on the piece of paper. This is especially helpful then if, let's say, that you happen to write down the wrong interval, the wrong numbers for the interval in this particular case. And if you just wrote down, maybe on your piece of paper you did something like this, 4, 6. That's the only thing you wrote. But the answer was actually, let's say, 15.3 is less than expected value of y is less than 20. How am I supposed to assign you any credit then? Well, you knew an interval was needed. Well, that's good. That shouldn't be too hard if I ask you for an interval. But how do I know that you were doing anything right at all? I can't give you any partial credit if you only wrote down this. If, however, you wrote down this first so that I know, oh, yes, you are looking at the correct formula for a confidence interval for the expected value y, then I can give you some partial credit, even if you got this answer incorrect. So, just to make sure it's clear, write the answer down and show me some work on every single problem. If you have time, only if you have time, you can write down some of your code as well. So for example, you could write down predict and then whatever code you use to get the, let's say, to get the interval. Okay? But that should only be done if you have time. So the way I would recommend doing the test is do all the problems with putting the answer down, showing work, and then if, let's say, there's 15 minutes left to go with the exam, well, instead of maybe turning in the exam, well, maybe go back and start writing a little bit of the code. Okay? But I don't want you to get overwhelmed with writing every single aspect of your code on the exam. Don't do that. Is there any questions? Okay, so again, you'll be using the computers here. If you have not already, please make sure before the exam that you can log on to these computers and that you're familiar with finding certain aspects of the stuff that's on these computers, like where is R? Where is TIN? Where is RStudio? Make sure you know how to find that stuff on these computers. Make sure a common problem that students have, well, I shouldn't say a common, but a problem that sometimes pops up, is that students have problems reading in data sets. Well, I would hope that before they came into class, they have read in a data set into R in the past. But too often, I run into situations where at the beginning of the exam, I have a student raise your hand saying, I can't read in this data. Well, it makes me wonder, well, did they ever read in data in the past? I hope so, if they've been doing the projects, if they've been doing the homework. So make sure that you understand how to read in data sets, especially if it's not even on your computer. Test, again, is closed book, closed note. You cannot access any of my lecture notes online. You cannot access any of the homework. You cannot access any of the projects. But what you can access are my R programs. So all these programs, on the R webpage will be made available to you. Again, this is I provide this as a way so that you don't have to memorize R code. But what this means, too, is that you should have a general familiarity of where to find certain aspects or certain things in my R programs. Let's say, for example, you need to do a confidence interval for the expected value of y, and just for some reason you can't remember the exact function that you need to use, or maybe the syntax. Well, without thinking about it too much, hopefully you realize, okay, that was in Chapter 2 when we did this, so that means, oh, I bet it's this high school college GPA Chapter 2.R program that contains the actual code for that. I can see how how Chris did it in class. Ah, there we go. And then copy and paste it into your program, make some changes necessary for your data set, and there you go. So you need to have some familiarity. If you're spending 5 or 10 minutes looking through all my programs trying to figure out how to do something, then you're not as familiar with the programs as you should be. Was there a question?
For reading in data sets, isn't it kind of different on that?
Is it what?
Isn't it different on a Mac?
I don't have, I've never used a Mac, so I don't know. I think in this class, this is the most Macs I've ever had. I think in the past I've had maybe 3 students at least that where I was made aware of in my, let's see now, my now 18 years of teaching, where they're actually using a Mac. That's not saying Macs are bad. It's just that's what I've come across. Obviously, we're using Windows-based computers here, so you need to know how to use a Windows-based computer to read in data. Do note that there are some issues with reading in Excel files depending upon 64-bit, 32-bit files and stuff like that. I will make everything a comma delimited file or a plain text file. Okay? So that you don't need to use RODBC, that package.
In terms of, for example, your program for the evaluation of the individuals contains the means test and the other one.
Yep.
And it needs additional packages in R. So all these packages are already installed? Or
They should be. And I will double check this right after class. If I remember right, my function will run on these computers. At the beginning of the semester every year, I always, ask our computer support person, I need these packages on these computers, and they should be installed. And I thought I checked it, but I will double check just to make sure. If there was ever a problem, you wanted to install some other package, you can still install packages here. Just the thing is that once the packages are, if you were to do it yourself, the next time that these computers will be rebooted, that stuff will be removed. Because they have various security things on here. So only administrators can install stuff, and that stuff will remain. Were there any other questions about that? Okay. As a reminder of what is allowed and what is or what is not allowed, let me say that again. What's not allowed for the test? Obviously, communicating with anyone in or outside this class. So don't be logged onto the chat room and communicating with other students in this class or outside of this class. Obviously, if you have my lecture notes open, that's a no-no. You shouldn't do that. Remember, I can see everything that's on your screen right up here. It's not worth taking a chance. Also, keep your eyes on your own computer screen. Obviously, you're sitting at this desk here in this kind of elevated room. You might look around your computer screen and look at the computer screen of the person in front of you. Please don't do that. It will be kind of hard to see as long as the person is using the normal size font. Now, that means, too, on your computers, don't use a size 40 font. Okay? Please don't do that. Anyway, if you communicate with others, have my lecture notes open, look at other person's computer screens, all that stuff I would consider cheating. Make sure that's clear. The only thing that you can have open on your computers are its corresponding R help, the internet web browser that's pointed to my course website, in particular the R web page, and also TIN or RStudio. Those are the only things you can have open on your computer. Oh yeah, the data set. So, you can have that open, I guess, in Excel or Notepad, depending upon the form. Because common delimited files by default usually open up in Excel. Okay, so that's the basics of the exam and its structure. Are there any questions about that before we start reviewing some material for the exam? Okay, let's review some material. So again, chapters 1 through 3. So chapter 1, it's very important that you know the basics of what the population is and what the sample is and the corresponding models for the population and the sample. In particular, there were some nice diagrams on page 1.7 and 1.10 of the notes that help explain kind of the big picture of what we're all trying to do with a regression model. Make sure you understand those diagrams. As I mentioned in the past, I've actually given some of those diagrams on tests before and asked students to basically explain them. Explain what they're representing. Just to make sure this is clear, obviously you need to know certain particular locations on our output that you generate, particular locations to find the important things that you need. Obviously, you know what B0 and B1 are, how to calculate them, what they represent. Well, they're estimates of beta 0 and beta 1. Of course, then how do you interpret then B0 and B1 as well? And then we looked at some properties of these estimators, such as the expected value of B1 is equal to beta 1. Why is that good? So make sure you understand that. We talked about MSE, the mean square error. What does this represent? What is it trying to estimate? Well, it's trying to estimate basically sigma squared. We also talked about how we can visualize what this MSE is doing by looking at a plot, and we also looked at in terms of that rule of thumb for the number of standard deviations, all data lies from its mean, how that MSE helps us to see how far these points are from our sample model. And lastly, in chapter 1, we also did that little R introduction. There are no direct questions from that R introduction, so don't worry about that. So chapter 2 now. One of the big parts of chapter 2 was understanding this thing called the sampling distribution of B1. I think oftentimes introductory students or students who are new to statistics don't necessarily understand the full implications of knowing the probability distribution for B1. The reason why it's so important is because this is what drives our ability to do any kind of inference. Because confidence intervals come from the fact of knowing what this distribution is. Hypothesis tests come from knowing what this distribution is. If we didn't know this distribution, we wouldn't be able to do inferences. So understand what the sampling distribution of B1 is, then obviously understand confidence intervals and hypothesis tests associated with this. In particular, doing a test of beta 1 is equal to 0 versus not equal to 0. And why is that important? Why is that particular value of beta 1 important? And we also talked about confidence intervals for expected value of y and prediction intervals for y. Understand how to actually do the calculations. Understand, well, why would one want to use a confidence interval here versus a prediction interval here? Well, again, it depends upon what you're after. Are you after the mean or are you after the random variable? Then in the second part of this Chapter 2 notes, we talked about SSTO, SSR, and SSE. These are three different sums of squares measure that help us understand the variability that's associated with doing a regression analysis. There was a nice plot, fortunately I don't have the page over here, there was a nice plot in the notes that really demonstrated what these measures are after. And why, we want, for example, a small SSE. How it also demonstrated how SSTO kind of measures your, let's say, your overall variability that you have. Gives you kind of a worst case scenario if you were to use just let's say y bar to predict what y is. And then we put these sums of squares measures along with other stuff in an ANOVA table. You make sure that you understand the structure of an ANOVA table, its different components, and what those components mean. And then this leads then into an F-test for what was actually the same hypotheses that we had earlier with a t-test. In a related, something related to all these different sums of squares was R squared. And this, really helped us understand, the amount of variability that's explained by the regression model. In other words, what are we gaining from doing the regression model? The closer to 1, the better. But just because it's not close to 1 doesn't mean that there isn't some gain. Like, for example, if I have an R square of 0.3 that says 30% of your variability is explained by X. Well, that's still 30% that you wouldn't have had before without knowing X. So 30% in some cases might be a good number, depending upon the application. A classic type of question to give on an exam like this, in fact, this is a question that I had, I remember on my very first tests when I was a student, when I was taking a regression course, is for me to, let's say, give you some output, maybe in a ANOVA table, for example, or maybe something from, let's say, summary mod.fit. Give you an output, and then I will actually remove some of the numerical values. And you don't have access to the data at all. And you need to figure out, based upon the context of the stuff that's surrounding those numerical values that were removed, what these missing values are. So, for example, maybe in an ANOVA table, I remove SSE. Based upon everything else that's in the ANOVA table, could you figure out what SSE is? No, if you know what the formula is, you can. So that's a classic type of question that's often given by instructors in a class like this. Doesn't mean I'm going to do it, so don't be disappointed if it's not on the test. I'm just saying that that's a classic type of question. Chapter 3. Now we're evaluating our model. And the first things that we did was just some simple diagnostics regarding X. In terms of, we want to make sure that there weren't, let's say, any kind of data entry errors, for example. And so we looked at some dot plots, box plots. And then we started getting into the more important stuff. I'm sorry, let's talk about this first. I also described what a semi-studentized residual was. Well, why do we want to do a semi-studentized residual? Well, the reason being is because it helps put it on a numerical scale that we basically have a better concept of what's unusual and what's not, essentially put. Between -3 and 3, we use an approximate normal distribution approximation. Then we started getting into stuff like this. How to check the linearity of the regression function. What that just basically means is, have we specified x correctly in our model? We just specified it as, well, x. But should it be x squared? And we looked at earlier today examples of how to make that judgment. Then we looked at the constant error variance. How can we make the determination of, well, is this assumption violated or not? And again, we spent some time today talking about that, so I'm not going to go into any more detail here. Then we looked at, well, how can we determine the independence of these epsilons? That's, again, an assumption of our model. Well, we do apply the residual versus time, for example. Also, we talked about how to check for outliers. Again, -3 to +3. But again, don't be too picky. If you have one that's, let's say at 3.1, that doesn't mean that you have to throw out your model, corresponding to our discussion that we had earlier today. Also, normality for the error terms. How can we check that? We have a variety of plots. And lastly, the addition of another predictor variable. How would you make that determination if it was needed? Now, on a number of these three that I checked here, we spent a lot of time talking about, once you've found a problem, how do you solve the problem? So please make sure that you understand, well, if I have non-constant error variance, how can I potentially solve the problem? And there's a variety of ways in this case that you could. Okay. So that's all I had specifically to say about the exam. What I would like to remind you is that and students have found this helpful in the past, but I just want to make sure that you understand that this is available. Again, since I'm recording everything that I talked about here today, that means that if you wanted to relive this experience of going through this review, you can. Obviously, you might be typing, writing some stuff down, and maybe you weren't able to pay as close attention to me as I was going through this, or maybe you just want to make sure that you understood what I said. Again, you can look at the review again. Usually, I post these videos, links to the videos by, I would say, usually by 4 p.m. every day. There's been a few times where I've had to wait in the evening because the video wasn't completed yet, but usually it's by 4 p.m. every day. Okay, so that's all I have to say specifically about the exam. Do you guys have questions? Yes?
Can you talk a little bit about the exact, the exam mark, that thing?
What's your question about?
Yes, because I really have trouble, sometimes to copy and run that first, and then, how to answer the question.
Just a second. So here's the function you're talking about, right?
Yeah.
Well, the thing is that before you use this function, it needs to be in R. The quickest way to get it in R is to come up here, you click Send File Source, and transfers it all to R. Notice also you see the actual function that's used to get that code into R, the source function. Another way that you could do it is just simply copy and paste all the code. Copy, and now I'm going to paste. That's how you get the function in R. Does that answer your question?
Yes, and And then how to change, like, if I have to change, like, the constant value test, how to change at the beginning or after that?
Well, it's just like any other function that you use. For example, with the LM function, you have argument names. And if you want to go with something other than the default, for example, if you do want the test, well, change the false to true when you run the function. So when I actually run this function here, so I'm not saying at this point where it's actually with the actual code, so let's say I'm running the function like this. So I've estimated some model, the results are a mod.fit, and I want to get that constant variance test. This is how I would run the function. Does that answer your question? Okay, good. Other questions? Yes?
Why does team doesn't highlight your own function?
I'm sorry, say that again?
When you use your function team, it doesn't highlight your own function.
Well, that's because I think what you're saying is that, like, if I were to, perhaps this is what you're saying, if I were to type something like LM, and you can see that, is that what your question? Why doesn't TIN do that? It's because TIN basically has, like, you can say, kind of like a dictionary inside of it for the functions that come with R. Obviously, this function doesn't come with R. I wrote it myself, so that's why you don't see that highlighting come up.
Because, for example, when you open the packages, there's kind of help
Yeah.
what parameters you want to have to.
Yeah, it's very, very nice, but that won't happen for any functions you've written yourself. It's, you know, there's like a dictionary, like you say, maybe that's not the best word to use, but like a dictionary inside of TIN where it has records of all these functions that come with R that allows the highlighting to take part. If you want highlighting, I guess, for my function here, why don't you contact the R main people who control it all and say, hey, this is a great function, why don't you do it? Why don't you put it? Other questions? Well, there's only about 10 minutes left, so I don't think it would be worthwhile for us to start Chapter 5, so we're getting to Chapter 5 again. So why don't we just call it a day? Again, feel free to post messages to the listserv if you have any questions. My virtual office hours are Monday nights. And well, good luck with your study.